it always confused me, though, when I was little. My parents said that. So I'll begin with a word of prayer. Dear Father, we thank you for this day again, Lord. Thank you for students. Just ask that you to bless this class today, Lord. In your name I pray. Amen. All right, so at last, the main event, the big theorems. So this is the so-called divergence theorem. Or Gauss's theorem. It states the following. It says that the surface integral over the boundary of some closed region, let's say E, all right? So here we're taking E, a simple solid. A simple solid, what that means in particular is that the boundary of E is simply connected boundary. And so one of the things that means is that E doesn't, this E, it's got no holes. I mean, it's solid. It's got no hole inside it, all right? So like a ball or a donut would be fine. You might think a donut has a hole in it, but not in this sense. You know what I mean? Like a torus would still be a simple solid. See, inside it, there's no holes inside it. This hole is outside of the torus. In contrast, if I had a spherical shell, and I can't do it justice, but like if you can, well, I don't know, imagine like a gobstopper, but somehow there was a way for ants to get inside, and they could eat out the middle of it. That would be like not simple. That would have a hole inside. I don't know. There's probably a better example you could think of. Simple solid, no holes. It's filled in inside the edge, inside the boundary. There's no holes. All right. So, a better example. A cube would be another example of a simple solid. This would be a simple solid, just a cube, all right? Anyway, so the flux over the boundary of a simple solid, and this is the theorem, is equal to the triple integral over the simple solid of the divergence of the vector field. Aha! So there was some reason we were talking about divergence before. Yes, there was. This is why we talked about divergence. Because in fact, it is connected to the question of flux in this rather surprising way. I will now work for you the problem that took us 10 minutes last class in about 2 minutes. Maybe it took us 20 minutes last class. I don't know. What was the example? We had the vector field. What was it? X squared, X squared, X squared, right? And we calculated the flux through what? What was it? It was this thing, right? We had the top, the bottom, the left, the right, the front, the back, right? Remember that? So this would be, E. So our S was the boundary of E yesterday, right? And we calculated it directly. We found it was 1. Did we not? The answer was 1? Right. Okay, so let's calculate it this time with the help of this sledgehammer of math, the Gauss theorem, the divergence theorem. So we take the triple integral over the cube, but the cube is 0 to 1, 0 to 1, 0 to 1, right? I mean, it's cube, so there's the triple integral setup. What's the divergence of this vector field? Six x. Very good. Wait a minute, no. It's 2x, yeah. You guys fished me in there for a second. 2x, thank you. Because, yeah, because, of course, the divergence of f, I'll remind you over here, is equal to partial x of x squared plus partial y of the y component, which is also x squared, plus partial z of the z component, which is also x squared. And, of course, this gives us 2x because this and this, 0. 2x. And then you got yourself dx, dy, dz. And so, yeah, that's 2x squared over 2 evaluated from 0 to 1, y evaluated from 0 to 1, z evaluated from 0 to 1, which is 1. Yep. What's that? Yeah, divergence theorem is really nice if you can use it. See, let's look at another example. Let's find the flux through the cone. So let E be solid cone. Right, so the boundary of E has two pieces, right? Like the top and the base. Now, the other thing I haven't told you yet, is this is kind of important. The divergence theorem assumes that the simple solid is positively oriented. What does it mean for a simple solid to be positively oriented? It means that its boundary is oriented out of the shape. All right? So to say that this is a positively oriented solid cone would be to assume that the boundary of E, the top, has got normals like this, right? And down here, you've got ds. And I could even tell you, and I want this to be the solid cone that, I guess I need to be a little bit more specific than that, right? Let's say phi equal to pi over 4, let's do pi over 6. And z greater than or equal to 0. Yep.
So for your first example with the cube, why can we assume that the cube is a simple solid since we're just doing the boundary of the cube? Doesn't it technically have a hole in the middle of it? Am I not understanding what you mean by it has a hole in it?
Well, this is the boundary of the cube.
Yeah.
And you're not wrong. That has a hole inside. But I'm not saying that the boundary doesn't have a hole inside. I'm saying that the simple solid doesn't have a hole inside. So the question is not whether or not the boundary of E has a hole. The question is whether E has a hole. And E is this, it's the filled-in cube. It's E that's the simple solid. It's not the boundary of E that's the simple solid.
I think he's just asking, can you assume like this cube in particular was filled in?
Well, that's what I'm saying from the start of it. Well, the filled-in cube takes the cubical shell that we looked at last time as its boundary. That's what I'm saying. So this is the frustration of language I was talking about yesterday. Yes. Okay. So now we're feeling it. I think maybe this is. I need to be more. I think my picture might be. Is that right? I'm sorry. I'm not feeling. I need this. This cone doesn't feel right yet. Let me stop and recalculate here for a second. The cone I want the cone to look like. I'm sorry. I want the cone to look like this. Okay. Sorry about that. So this is the cone I was interested in. And let's say it has radius r, and let's suppose it has angle phi equal to pi over 6, all right? So that's the cone I had in mind. So let's say the solid cone is E. the boundary of E has two pieces, right? It's got the cone, cone base, let's say, and it's also got the top disk, right? Let's call this thing S1. Let's call this thing S2 for the sake of discussion, right? So, all right, so if we're giving the solid cone positive orientation, that means that the ds here should look like a this. Up here, like a this. Now, how about, okay, so for S1, what's our ds, by the way? For S2, what's our ds? I'll do the easy one. S2, you got yourself dx, dy, z hat. That'll do just fine. Or if you don't like that, you could do r, dr, d theta, z hat. You got choices. The point is it's flat. So I can use any of my favorite surface area elements in the plane. Those work just as well for parallel planes to the xy plane. Because you can use x and y as a parameter for such surfaces. What about the ds1, if you will? This much I know. The direction of it should be phi hat. What was the, do you guys remember what the scalar surface area element was there? What parameters do we use to parameterize a cone? We freeze out the phi, right? So the parameters are rho and theta. So I think you could even derive the ds if you wanted to try. You could look at like a little d theta, right? And a little d rho, d theta. So we'd have d rho, and what d theta is not the arc length along this sweepy thing. How far is that from the center axis? What's the radius of that sweeping? It's little r, right? So we've got r d theta, which, by the way, is rho sine phi d rho d theta. So we'd have rho. And what is sine phi here, though? It's 1/2. So what we got here is we got a rho over 2 d phi d theta. Now, I don't need to do any of this to actually do the problem I'm about to do. I'm just showing you what's involved in the setup of the cone because I think you still need to see it. All right? So if we were going to calculate the flux of a vector field over the boundary of the solid cone, what would it look like of a vector field F? We got two pieces, right? We've got the integral over r less than or equal to big R of F dot, r dr d theta z hat. That gives me the top piece plus the double integral over, the cone. Let's call it S1, and that would be F dot. If you'll allow me this slightly hybrid notation, I hope it's okay. Rho over 2 d rho d theta. Can you tell me, though, oh, and I forgot my phi hat. I mean, certainly we could do these integrals for a given vector field, right? We could. What should rho and theta vary over for S2? I'll do theta. Hey. Should have taken it from you. That was easy picking. What about rho? I'll do half of rho. Haha. I mean, rho is 0 down here, right? And up here, what's rho equal to? It's not r. R tan phi. Here's the picture I would draw to make sure you're right. This is rho max. This is r. This angle's pi over 6. And what do you tell me? Rho is equal to what?
Wait. Yeah. Would it be R tan phi?
You're saying rho is equal to the tangent of pi over 6 times r? No. I don't think it's a tangent. I think it's a sine, right? The sine of pi over 6 is equal to the opposite, which is r, divided by the hypotenuse, which is rho max. I mean, sine of, and of course this is a half. So in fact, our max rho in this context would be 2r. Anyway, my point is we could set up these integrals, but they're a pain. All right, now let's actually calculate the flux of a, let's say the vector field, I don't know what you guys want. F equal to, let's say, z squared, xy, z. Calculate the flux of that vector field through the boundary of the solid cone. So let's go for it. We got integral over the boundary of E of f dot ds that is equal to the triple integral over the cone of partial x of z squared plus partial y of xy plus partial z of z. dv. So what do we got to integrate here? Integral over the cone, solid cone rather, and that's 0. What's this? X, right? What's this? 1. Look at the cone. How do the values of x distribute themselves over the cone? Is there a left and a right as it concerns x? I mean, is there a front and a back? Maybe the front of the cone is positive x, the back of the cone is negative x, but they're equally situated. I can tell you without doing any more calculus that the integral over x over that volume is going to be 0. Now we could work it out, but it will work out to 0. That's going to happen. How should we do this integral? This is a solid cone. What's its description in terms of spherical coordinates? 0 less than or equal to rho, less than or equal to 2r, apparently, right? 0 less than or equal to theta, less than or equal to 2 pi. 0 less than or equal to phi, less than or equal to pi over 6. This is quite clearly an integration we should do with spherical coordinates. So let's do that. 0 to 2r. 0 to pi over 6, 0 to 2 pi. My x is rho cosine theta sine phi plus 1. What's my dv? Rho squared sine phi d theta d rho, d phi d rho, given the order of integration that I have here. All right, let's clean that up a little bit. Integral from 0 to 2r, integral from 0 to pi over 6, integral from 0 to 2 pi. What do I got? I got myself a rho cubed cosine theta sine squared phi, which looks awful scary, plus rho squared sine phi, parentheses, d theta, d phi, d rho. But you can already see when we do the integral over theta, what happens? We get a sine theta times rho squared sine squared phi, but that sine theta is evaluated from 0 to 2 pi. So in the very next integration, you can see that this piece goes to 0, as I told you from symmetry reasons. On the other hand, rho squared sine phi, what happens when you integrate with respect to theta, that term? Integrating theta gives us a 2 pi rho squared sine phi d phi d rho, which I'm going to factor since there's no, the bounds are nice here. So we've really got integral from 0 to 2r of rho squared times the integral of 2 pi sine phi d phi from 0 to pi over 6. So what's that give us? That gives us rho cubed divided by 3, evaluated from 0 to 2r. And this gives us 2 pi minus 2 pi cosine of phi, evaluated from 0 to pi over 6, which is equal to 8r cubed over 3 times, what we got here? What happens when you plug pi over 6 into cosine? You get what? Minus 2 pi square root of 3 over 2 plus 2 pi. There you go. That's the flux of this vector field through the surface of the solid cone, positively oriented outward. Questions?
So all of that flux came from the 1, nothing from the x's?
Right, yeah. So it goes. Let's see here. This vector field, if we think about you could ask yourself, once you have this, you can ask yourself more complicated questions like, that's the total flux, right? So notice that if you calculate the flux through either the disk or the cone piece, you can subtract that from the total to find out what the other one is. There's a lot of problems built on this idea. Kind of like a whack-a-mole idea, right? Sort of like that. I don't know. Usually the disk is easier to do the calculation in this kind of problem, right? Because the disk is flat. The disk has the normal to the disk is what? Like z hat, right? So if you actually calculate this piece, it's actually relatively simple for that vector field C, because this integral just simplifies to what? Z, well, z dA z hat, basically, this integral. What's z equal to on that disk, though? What is z at the top of the cone? That's the other thing here, z top. That's this distance, which we also have not calculated yet. But it would be given by cosine, right? So you could say cosine pi over 6 is equal to z top divided by rho max, I suppose, which is z top over 2r. So in fact, z is equal to what there on the top? Solving that, we get square root of 3 over 2. That's the cosine of pi over 6, and then times 2r. So if you look at that, this is straight up equal to the integral, and this is, I'm sorry, the z hat's not even there. It's z hat dot z hat, right? Which is, so this integral just simplifies to that because z hat dot z hat is 1. The other two terms don't even matter because when you take the dot product of the surface normal with that vector field, you just pick up the z. But we're on the top of the cone where z is equal to the, square root of 3 times r. So you just plug in square root of 3 times r, and look at that. Well, that's just a constant, so I can tell you that the top gives us, square root of 3 r times the area. What's the area of this? Well, that's pi r squared, right? So there you go. That's the flux of this vector field through the top of the cone. And so if you take this animal over here and you subtract that from it, that gives you the flux through the sloped side. Yeah. All right. Well, there you go. That's a flavor of what we can do with the divergence theorem. I have not begun to explain to you why on earth this theorem should be true. It is most mysterious, is it not? This theorem. But I think you can see that if you can see how to apply it, it is very labor saving because it's much easier to calculate a volume integral than a flux integral, especially when your shape has different faces and different cases, which means multiple integrations, right? We already saw this kind of economy of calculation when we were studying Green's theorem, right? Where we could trade the integral, 4 line integrals around the edge of a square for a simple double integral of the appropriate function over the filled in square, right? It's the same kind of theorem, really, right? This is a lot like Green's theorem. The other theorem, and this one's even weirder, is Stokes' theorem. Stokes' theorem says that the integral around the surface integral was me? No. It's all Josiah, right? Was
My fault.
it's mostly Josiah? Okay. All right. I'm going on. All right. So if we take the flux of the curl, and okay, again, here S has got to be simply connected, at least to start with. In fact, truth be told, you can add holes in both of these theorems, provided that you expand your idea of what the boundary is to include appropriately oriented interior holes in either the simple solid or the surface. In other words, there's an analog of that annulus theorem that we saw for Green's theorem in these contexts as well. But let's stick with the simple case to start with. So anyway, simply connected, which means this surface could look something like that. It's got no holes. And it's positively oriented, which means that if you think about little Mr. Top Hat here, walking along the edge, he's walking this way. Because he's got to be walking such that the surface is on his right, his left. Okay? So that's the positively oriented boundary, like so. So the surface integral of the curl is equal to the line integral around the boundary of the function. This is Stokes' theorem. And this is a lot of the reason we talked about the curl. Both the divergence and the Gauss theorem are very important to physics, especially electrostatics and magnetostatics. Let me talk about the application of this theorem to conservative vector fields. What was one of our theorems for conservative vector fields? Actually, what was the theorem for conservative vector fields? On, let's say, U, a subset of R3. Let's suppose that this is open, and what else did we say? Simply connected, if we add that. In fact, much of the theorem I just stated for connected, not simply connected, but we could state the theorem for simply connected, because that was the fourth case. So let's just state the theorem for simply connected. Theorem. Conservative vector fields on this can be characterized via any of the following four spiritual laws. No, wait a minute, just four laws. Number one, that there exists a little function f from u, last u, to the reals, such that f is equal to the gradient of f. That, in fact, was our definition of conservative vector field, that there exists a potential function on u, which we take the gradient of, we get back to the vector field, right? Number two, f is path independent on u. That means that, you know, and u is, again, a three-dimensional thing, so my picture's got to be a little bit more here. It's a blarb. So you got 2 points, right? You take one path, you take another path, c1, c2. We've got the integral over c1 of f dot dr equals to the integral over c2 of f dot dr, right? And it doesn't matter which pair of paths you pick, c1 and c2, as long as they begin and end at the same points and they don't leave the set u, we have that these integrals work out to the same. That's path independence, right? That's the definition of path independence. 3, that the closed integral around any loop in u, f works out to what? The conservative vector field, the integral around the loop is 0, right? And then 4, a strangely technical result, right? A strangely technical result, which was that if the curl of f was equal to 0 on u, these are equivalent conditions. If you give me any of 1, 2, 3, or 4, I can get the other. Now, it's easy to see that 1 implies 4 because the curl of the gradient is 0. That's a simple thing to work out from just the properties of partial differentiation and definition of the curl. That was not hard for us. But how would we prove that this implies, well, let's not pick on that. Let's try to prove this. 4 implies 3. How do we prove that? Think about it. So take your open, simply connected space. I'm going to view it like a box, just for the sake of me making a picture you can see. Take any loop in this box, which I'm calling u. I mean, I'm just using a box for the sake of visualization, but it's an open, simply connected space, which we've called u, right? You take any loop in here, right? Take any loop. What does that loop do? It encloses a simply connected surface, which is also inside u. That's part of the terms and conditions of what I mean by u being simply connected, is if I take a loop, I can fill it in like this. I can fill in the loop, S, right? And the loop will just be the boundary of S. I can do that for any loop. Any loop in U, I can do this. I can find a surface which the loop appears as the boundary of. And that means I can apply Stokes' theorem, right? So the integral around the boundary, Yes, indeed. Of f dot dr is equal to the surface integral over S of the curl of f dot ds. So you see, if we know this is 0, then we get 0. And that is why 4 implies 3. We need to be able to apply Stokes' theorem to basically to surfaces that appear inside these loops. It's kind of neat. Did you guys learn Faraday's Law in Physics 232 yet? Faraday? You've talked about induction, Lenz's law, the EMF induced. What was the rule for how's it go? What's the formula for the voltage? How's it go? I need some place to write. Over here. If I recall correctly, the voltage, right, is equal to minus the change in magnetic flux per unit time, right? A changing magnetic flux through a loop induces a voltage around that loop. That's Faraday's law. It's an experimentally determined fact. So this is actually, essentially ddt, well, you could say partial t of, well, there's a minus, the integral over some surface of the magnetic field dot ds. See, because this is the magnetic flux. How do you calculate voltage in terms of the electric field? That's the integral of E dot dr around the boundary of this loop. So what do we have? We have that the integral of E dot dr is equal to, this changing rate, time rate changing, the time rate change of the flux through a loop. So this is the principle motors work on, right? If you have a loop of wire and you have magnetic field lines going through it, you can, if you increase or decrease the flux, you change the flux through the loop, it will induce a current. This is induced current from changing magnetic flux. This is Faraday's law. This is the specific mathematics of it. The induced, why is the induced current? Where's it coming from? It's coming from the electric field pushing the charge in the wire, right? This electric field is pushing charge in the wire and creating that current, the induced current. Question: is this induced electric field conservative? Well, this is equal to the surface integral. I mean, the answer to that question is no. It's already clear here. This is a loop. The integral around a loop of the electric field is something non-zero. This is not a conservative electric field. This is a non-conservative field. And you can see this interplay quite beautifully. This is Stokes' theorem. The surface integral of the curl of the electric field, right? Well, that's equal to the surface integral of minus partial b partial t, moving the derivative inside. But this holds for arbitrary surfaces, which reveals to you one of the true equations of electromagnetism, namely this: the curl of the electric field is minus the time rate change of the magnetic field. This is Faraday's law in differential form. It says that a changing magnetic field leads to a non-conservative electric field, an induced electric field. And in fact, the electromagnetic fields are not separate. They're part of one entity that kind of is a whole. We talk about the electromagnetic field because you can't think about the electric without the magnetic and vice versa. They feed into each other. This is how light works. A light is an electromagnetic wave. It's going electric, then it's going magnetic, then electric, then magnetic, then electric, then magnetic. Transverse wave, one bouncing off the other. Anyway, all of these things, all of these stories I'm telling you, are woven in the tapestry built with these two theorems. It's all about the divergence theorem and the Stokes theorem. We'll do examples of this later. It's just, it wears me out to do an honest to goodness with numbers and stuff example of this. Like, it wears me out. It's going to take me 10 minutes, and it's a drag. But you notice either one of these theorems is great. If I have this on the, the next test and the final, think about what you're being tested on. You've got surface integrals, you've got line integrals, you've got volume integrals, right? Everything in the whole course is woven into these two theorems. So that's why it's important to understand them, because if you understand these two theorems and how to actually do problems in them, you've actually understood the whole course. This is the goal of Calculus 3, is to understand these two theorems, actually. Because that's just a sneaky way of saying, I want you to understand everything we've done up to this point. That's all. Anyway, have a good weekend, you guys. That's it for today.